Hey there. This is a screencast where I'm going to work through a word problem for you that puts to use ideas of the antiderivative that we've been talking about in class. So, here, let me write it down. Ooh, let's use black. So imagine someone's driving a car on a freeway. Let's say it's the 101. And the driver sees a raccoon in the middle of the road. About 350 to 375 feet ahead. The driver slams on the brake. So when you slam on the brakes, you decelerate. And so the driver is going to do this as safely as they can. So the maximum safe deceleration of a car, assuming good roads, good tires, is agreed to be about 15 feet per second squared. So here's the question. Will the car stop in time to avoid hitting the animal? Okay, this is the word problem. This is what we were going to use some calculus to solve. And you can tell from the problem, this is a distance, velocity, acceleration problem. We've got a velocity here, we've got a distance here, and we've got an acceleration here. And we're going to use these to answer the question. Is there a chance the car is going to hit the poor animal, or is it going to stop ahead of time? So here's our work. We're going to define some functions. So we're going to define a position function, a velocity function, and an acceleration function. So like s of t, let's say this is the position of the car. Okay, and to be more specific, let's say the distance the car has traveled after the driver hits the brakes. Okay, so here we're saying t is the number, or t is the time after the driver hits the brakes. Okay, so t equals 0 is the time the driver hits the brakes. Yeah, so homonyms are terrible, right? So if s is our position function, okay, then we'll have a velocity function and an acceleration function. So v is going to be the velocity of the car at time t, okay, t seconds or t, however, t units of time after the driver hits the brakes. And a of t is going to be the acceleration of the car at time t. Okay, so there's a couple things that, so this is the general framework, right? We've got a position function s, a velocity function v, and an acceleration function a. So one of the things we know is that velocity is the derivative of position. So this is a relationship that's true. We also know that acceleration is the derivative of velocity, but that is then the second derivative of position. So here's some facts that we know in this situation. So one question that we need to hammer out or make a decision about is, what are the units? So we need a unit on time, we need a unit on position, we need a unit on velocity, and we need a unit on acceleration. Okay? So in the problem, we're told the first unit that we're given is about velocity, and that's 70 miles per hour. So the unit is miles per hour, miles divided by hour on that number. The other unit that we're given is feet. Right? The animal was 350 to 375 feet ahead of the car before the driver slams on the brakes, or when the driver slams on the brakes. And then the other unit is acceleration, and that's given in feet per second squared. So we have to decide what units we want to keep, and if is there anything that we want to change. So nothing was said about t. T is a variable we're introducing into the problem. So we can, well, what do we see here? We see seconds as a unit here. We see hours as a unit here. There's no time in the position. So you can choose hour or seconds, whichever one you want to use. But I'm going to choose seconds. Okay, let t be the number of seconds after the driver slaps on the brakes, because we all know that bringing a car to a halt if you're driving at a high rate of speed is not an event that is measured in hours. It's measured in seconds. So this is an appropriate unit given that context. So what that means is that we're going to want to change this so that that hour down there is seconds. So we're going to have to convert some units. But let's see, what else do we have to look at? So we've got feet here, we've got miles here, we've got feet here. Well, it looks like the feet are going to win out because it's occurring twice. And so it looks like we want to change that to feet. So the only units we're talking about are in terms of seconds and feet. So I guess that means we need to convert 70 miles per hour into a quantity measured in feet per second. Okay, so you could go online to Google and find a web page that'll do this conversion for you. But let me remind you how we do this by hand. So we start out with 70 miles per hour. And we're going to treat the conversion of these two different units, the miles unit and the hours unit, separately. We'll convert miles into feet, and then we'll convert hours into seconds. So to convert miles into feet, I want feet to be in the numerator and miles to be in the denominator, so that the units themselves will cancel, and I'll be left with the unit feet. And you can look up on Google, there's 5,280 feet per mile, so that's our conversion factor. So we're done with that conversion. Now let's convert hours to seconds. So hours in the denominator, so we want hours per minute. So there's 1 hour for 60 minutes. Right, so the hour units will cancel, and I'm left with the minute unit. But I don't want to be left with the minute unit. I want to be left with the seconds. So there's 1 minute in 60 seconds. So the units cancel. And now the only units I'm left with are the feet units in the numerator and the second units in the denominator. Once I multiply all these numbers together, I will have a number whose unit is measured in feet per second. So let's do that. So what do we get? So in the numerator, I've got 70 times 5280 over 60 times 60. That's feet per second. And if you want to use a calculator, or if you want to use Google or something, you can go ahead and figure out what this number is. I did it in a nerdy way I won't bore you with, but you can reduce this to 308 over 3. And that's approximately equal to, well, actually it's not approximately, it's exactly equal to 102 2/3 feet per second. So that's how fast the car is traveling. 102 2/3 feet per second. Okay, so good. We've got everything in terms of, we've identified units, we've converted our miles per hour into feet per second, and I think we're ready to go. So now I want to come up with the functions for position, velocity, and acceleration. If I need to. I'm not sure if I need to, but I know there's this relationship. So let's look at the scenario. So you're driving down the 101. So you're driving on a straightaway. And at some time, t equals 0, you're at this position. And the animal is here. I don't know how to draw an animal here. I guess I said it's a raccoon, so the raccoon's here at someplace 350 to 375 feet. And your car is traveling this way. Okay? So what's happening? Well, S of t is giving you your position on this line. And so your car is moving to the right, and so S of t is getting bigger and bigger and bigger. Right? If we're thinking about the 101 as being a real line with numbers on it. Okay? So your velocity is how fast your car is moving, and it's slowing down because you're on the brakes. But let's think about acceleration. We're told acceleration is, or deceleration is 15 feet per second squared. So when I decelerate, I'm making my acceleration go down. So if you remember, acceleration is the derivative of velocity. I want my velocity to be decreasing. So if you think about what a graph looks like when its values are going down, its tangent lines all have a negative slope. So deceleration for me means that this number is going to be negative 15. Okay? And as long as I've got my foot on the brakes, my deceleration is constant. So this is my deceleration function, my acceleration function, negative 15. And we know the units are feet per second squared. I'm not going to write that because we're doing math now. So let's look at the velocity function. So because acceleration is the derivative of the velocity, we know the antiderivative of acceleration is a velocity function, and I'll put a constant of integration there. So to find the velocity function, I need to antidifferentiate negative 15t. And the conversations we've had about antiderivatives will quickly lead you to say this is an antiderivative. This is the general antiderivative. But what we don't know is what's this constant here, c. We want to find a specific function. Right now this describes an infinity of functions. We want to describe a specific one. To find the specific one, we're going to use information that we were given in the problem. So we were told that at the moment the driver hit the brakes, when t equals 0, the driver was going 70 miles per hour, and we computed that to be 102 2/3 feet per second. So we know that. Now, given our computation here using the antidifferentiation, we also know that at 0, plugging 0 into that function, our velocity is given by this expression. Well, that's 0 plus c, which is just c. So here I've got two ways to describe the same thing, v at 0. that means that the things on the right side must be the same. So c must be equal to 102 2/3. So this tells me that my velocity function is negative 15t plus 102 2/3. Right? So here I can figure out how fast I'm going at any one time. Now, what are we interested in the problem? We're interested in whether or not this car hits this animal, and we don't want it to hit the animal. We want to know, well, you can decide if you want it to hit the animal. We want to know if it hits it. So we want to know when the car stops. So a car stops when its velocity is 0. So we want to solve v of t equals 0. Okay? When does the car come to a stop? All right? So let's solve it. So I'm going to say 0 equals v of t, and v of t is this. So adding 15t to both sides, I get this. Now I'm going to flip to the next page to continue the computation. So I'll divide both sides by 15. And 102 2/3 is the same as 308 over 3. So my number here is 308 over 45. And you can use a calculator to see that, or do it longhand if you're like me. And we get 6.84 repeating. So we can round that whenever we want to. So remember, this is in seconds. So it takes the car 6.84 seconds to come to a complete stop. Okay? Is that the answer we're looking for? Yes and no. That's part of the answer. What we really want to know now is, where did the car stop? Okay. So that is, what's the location of the car when it stopped? So what is S of 6.84? Right? At the time it stops, what's the position? How far did the car travel? So this means we need to find an expression for S of t. But luckily, we know v of t is S prime of t, and we know v of t is minus 15t plus 102 2/3. So if I anti-differentiate v of t, I'll get S of t plus a constant. Okay, so that's how I'm going to find S of t. So here's v of t. Let's do it. The antiderivative of negative 15t plus 102 2/3 dt is, now I'll let you go and check to see that the power rule for anti-differentiation says the first term is going to look like that. I'm going to rewrite the second term in this way. All right, and so this is what we get for our position function, right? This is S of t. All right, so these are all possible candidates for S of t. I need to find the S of t that works in our case, in our application, in our word problem. So I need to figure out what C is. So on the one hand, I know that S of 0, if I plug in 0, to my formula, I get this. And so the first term goes away, the second term goes away, and it means I'm only left with C. On the other hand, what do I know about my position when I put on the brakes? So I'm going to page back a couple of pages so we can look at this picture. So look at the top of the page here where I drew the real number line. This is the scenario. At time t equals 0, we've got the car. That's when we put on the brakes, or the driver puts on the brakes. I'm going to page back one more time. Well, actually, and one more time. And S of t, here's the definition of S of t. It's the position of the car, the distance the car has traveled after the driver hits the brakes. So at time t equals 0, it's when the driver hits the brakes. So how far has the car traveled at the instant the driver hits the brakes? And the answer is 0. Right? So the instant the driver hits the brakes, the car hasn't traveled any distance from where it was when it hit the brakes. So these things together tell us that for the purposes of the position function, c is 0. Okay. So let's write that down. We have S of t is minus 15 halves t squared plus 308 thirds t plus 0. Okay. But I'm going to get rid of that because that's nicer. All right. So why are we doing that? Well, we want to know what's S of 6.84 repeating. Well, let's plug it into our function we have now. It's negative 15 halves times that squared plus 308 over 3 times that. And if you figure that out, you get approximately 351.348 feet. That's how far the car travels. The car travels 351.3 feet after the driver hits the brakes. So, since the animal was between 350 and 375 feet away from the car when the driver saw it, so we're not sure if the animal is okay. All right, because the car travels slightly more than 350 feet. So this is a good example of the way calculus is used in the real world, antiderivatives, in the context of position functions, velocity functions, and acceleration functions. And make sure you study this problem. You know how each step is working. You can do the unit conversions, you can do the antidifferentiation, and you understand how each function is related to the previous function and how they all come together to answer the question posed by the word problem. All right, see you next time.